Hey everyone, and welcome to The Explainer. Today, we're going to do something a little different. We're going to tackle a subject that, let's be honest, scares a lot of people: university-level calculus. And we're going to do it by solving a real question from a final exam.
Okay, so where did we get this challenge? Right here. This is an official calculus exam paper from 2017. So this isn't some made-up textbook example, nope. This is the real deal, exactly what students were looking at on test day.
So, what does it really take to solve one of these things? We're not going to try to solve the entire exam, don't worry. We're just going to zoom in on one single question and see if we can decode the language of higher math together.
And here is our challenge. It's question 3, which I'm calling the vector riddle. Now, it's a multiple choice question, which might sound easy, but the real magic is in the journey we take to find that one right answer.
Here it is, exactly how it looked on the page. Now, if you're not deep into vector calculus, this probably looks like some kind of cryptic code, right? But let's break it down and translate it.
So when you strip it all down, here's what it's really asking. We've got two vectors, we can call them A and B, and the question wants us to find something called the projection vector of A onto B.
And that is the absolute key to this whole puzzle, isn't it? Before we even think about touching a formula, we have to get our heads around what a projection vector actually is. So let's do that first.
And you know what? To understand this, we don't need any complicated formulas just yet. All we need is a really simple analogy that's going to make everything click.
All right, I want you to picture this. Imagine two arrows just floating in space. That's our vector A and vector B. They start at the same point, but they're pointing in totally different directions. Okay, you got that? Now imagine a giant spotlight is shining down, and it's positioned perfectly so that the light rays are hitting vector B at a perfect right angle. The shadow that our first arrow, vector A, casts onto the line of our second arrow, vector B, that shadow is the projection vector. It's that simple. It's basically just asking how much of vector A is going in the same direction as vector B. It's just a shadow. Okay, so now that we get the idea, the whole shadow concept, let's see how we turn that idea into an actual step-by-step solution.
So here it is, the official formula. And yeah, I know it looks a little scary with all the weird dots and bars, but trust me, we're just going to break it down into tiny, manageable pieces. We're going to solve this thing in just 3 easy steps. First, we'll figure out the top of that fraction, then we'll figure out the bottom, and finally, we'll just stick it all together to get our answer. Easy!
All right, step 1, the dot product. This sounds way more complicated than it is. We just multiply the matching parts of our vectors, the i's with the i's, the j's with the j's, and so on, and then we just add up the results. And since vector B doesn't have a k part, that's just a 0.
And after all that, what do we get? The number 6. That's it. Our first piece of the puzzle is just the number 6. See? Not so bad.
Next up, we need the bottom of the fraction, the magnitude of vector B, squared. This is basically just a fancy way of figuring out the vector's length. We square each part of vector B and then add them all together.
And that gives us our second piece of the puzzle, the number 20. So we've got a 6 and we've got a 20. We're almost home.
Now for the final step. We just plug our two numbers back into that formula we saw earlier. We've got 6 divided by 20. That little fraction tells us how big the shadow is. Then we just multiply that fraction by our original vector B.
And after we do that little bit of arithmetic, we get our final answer. This is it. This vector right here is our calculated projection, our mathematical shadow.
So we have an answer, we did the work, we followed the steps, but was it the right one? Let's go back to the original exam question and see if all our hard work actually paid off. And there it is. Would you look at that? Our vector, 1.2i plus 0.6j, is a perfect match for option Aleph, the very first choice on the exam. We did it. We actually solved a university-level calculus problem.
But that leaves us with the big question, right? Why does any of this matter? I mean, who cares about calculating mathematical shadows when you're not sitting in an exam hall?
Well, what's so incredible is that this shadow math is the hidden engine behind stuff we see and use every single day. It's what video game engines use to figure out realistic lighting and shadows. It's what physicists use to calculate forces. It's how computer graphics project a 3D world onto your flat 2D screen.
And it just goes to show you, math isn't just about numbers on a page. It's a hidden language that builds and describes our world. What started as a cryptic line of symbols on an exam paper is actually a core instruction for how we create entire virtual realities. It really makes you wonder, doesn't it? What other secrets about our universe are just waiting for us to find the right formula?